All right, we're gonna get to work on the differential equation visualizer animation thing that I've been doing for the jam. This is the last day, so I did Monday, I did Tuesday, and I'm doing today. If you see here, I'm still making sure everyone knows you have the opportunity to support and become a member at the Mr. Fourth Lab, and you get stuff like devlogs. You can hang out on you get devlogs on the Discord, and you could uh, interact with other people there who are supporters if you want. If you become a member, a lot of my in videos, we're still working on this, but a lot of my videos are going to be indexed, and we're going to build out to the point where we have pretty much all the videos that I did on YouTube and that I do in the future on YouTube will be indexed there. That's really cool. If you're not familiar with the indexing system that Miblo does, it lets you search through all the videos, find whatever you're looking for. If it's memory management or graphics or my more esoteric stuff like the build system and the wave file format stuff. You can just search through it and find exactly what you're looking for, jump to the spot in the video that you want. It's a really convenient way to use my video library. And you also get access to stuff that's in development that is not usually public for everyone else if you become a member. So what I'm working on today, it won't be public probably for a few more days. I'm going to try to take the differential equation viewer and make a packaged up public copy of it in a few days. But if you wanted to get to it right now, you could do it in its current form as it is if you were already a member. So consider that. It does help a lot. I do a lot of the stuff that I do for free. I just put out a podcast today. I just put out a new podcast episode as well with Abner. So if you're done watching my stream and you want to learn some about Abner's terminal click stuff and hear some of his new feature announcements and stuff, definitely go check out my podcast, and you'll see I also put that out for free, and that's all possible if enough people were to become supporters and members. That makes a lot of the stuff that I do possible. So think about it. It's helpful. For today, we are working on this thing. Now, it's already looking pretty cool. As I was staring at this yesterday and during the pre-stream today, I did notice that there's sort of a strange phenomenon. You see these little, I don't know if you can see them on Twitch super easy, but there are little points, little spots show up that they're not trails, they're just by themselves a singular point. And I don't know if what's happening is that things are spawning in and then dying right away, or if they're shooting outside of the edge fast enough to that we only get one point there and then the trail is just a stationary spot. It's really not clear to me what's going wrong there that's creating that effect. So I'm trying to think of how we could isolate what that is and debug it, because it is kind of it's like an artifact. It definitely doesn't look right. See, there's just a bunch of little points living right there. Now, I imagine that what's probably happening will be visible if we were to look at all of our look at how many of them there are right here. How is that happening? What are those? That might be from the density killing thing. So here's my suspicion. I'm going to tell you what I suspect we're seeing. Let's pull open the, we're still building DiffyQviz. All right, we pull open DiffyQviz and we look at what happens when we kill a particle, whether it's, yeah, so right here I kill a particle by stopping it. So I'm only looking at the moving particles, and I'm allowed to tell a moving particle to stop. Once I've stopped a particle, it still has to continue stopping for several frames, because if it has a trail, then then that trail is still supposed to sort of fade away while the particle is coming to a stop, right? Even if I kill the head of it, I don't want the whole thing to blink away instantaneously. So the stop tells the trail to keep going, but I think what must be happening is that when I start a particle, I kind of just assume that it's not going to die before the full trail length has been expressed, right? Like, and I don't assume, if I have 16 slots for my trail, I don't assume that it's going to be less. I always assume that it's going to take more than 16 frames, that I'm going to get 16 unique points, that I actually have a trail of length 16. And the way I assume that is that I'm always setting the trail end while we're updating positions. I'm always setting the trail end to the spot right after the trailhead, but that's actually not super accurate if I think about it. The there's something a little bit off about thinking about it that way. Um, so let me think. What would be more accurate to do is to say when the particle spawns in, its trail head and tail and end are like at the same spot. The trail end is right right they're like at the same spot, and then whenever I write a new position into the trail, I increment the head once, possibly looping it around the buffer if necessary, and then I write into that position. And then what I do is I just keep writing that. It's not until the point where, at first, what should happen is the trail end should just be stationary. It should stay where it started. Trail end equals trailhead. So it starts off empty. The first point I write, by giving it a position delta, increments the head, but instead of just updating the end to go to the spot that says the whole trail buffer has been used, what should happen is, if the trail end is equal to the trail head, so what that would mean is that once we're like going along, if we're getting to the point where my trail end is here and my trail head is here, I increment the head by 1, I write into that position, then I have to bump the trail end up again, right? I have to keep saying, the trail end has to be 1 past the trail head. But when it starts, this will make it so that the trail end can stay there and the head can grow towards it. Let's see what that looks like. Okay, I think that might have done it. I think I'm not seeing those little points anymore just sitting around. For reasons I don't entirely understand. Oh, there are some points there. Okay, now they're showing up still. So it took them a minute, but now they're here again. What are those? I don't exactly know. There's a lot of them, too. I want to fix one other thing. I keep noticing that, like, when I start the animation... Watch this. If I start the animation, my mouse disappears. No mouse. Now, to get it back, like, I have to click, move my mouse off, and click off, and then when I come back, the mouse is there. It feels to me like I need to do... yeah, let's just do no... Don't hide the cursor on me. There we go. Okay, that'll make life easier. This isn't for rendering an animation, so having the cursor on the screen is actually desirable. But yeah, we want to figure out why we're getting little specks like right there and there. So these could make sense if it's very slow moving and it gets killed, but it should still... Hmm. Okay. So I want to um I'm going to use the fact that we have input to help here. When we have a key down, we'll use input key space with no modifiers. And I'm just setting this up so I can put a debug breakpoint right there. Remedy is still up and ready to go. .975. Breakpoint right there. Okay, cool. So I can put down a breakpoint. I can stop it whenever I want to. So let's wait until there's a good number of them on the screen. Okay. And then I want to go into vars here. And my goal here is to figure out if I can see inside the particles an explanation for why it looks like that. So I have stopping particles. Yeah, this is going to be hard because I can't very easily visualize all the data. But let's keep trying. So we're going to look at the first particle. We're going to look at the first particle's trail. Which has 16 spots in it. Like this. So this one isn't one of the problems because it's not stationary across its trail. So let's keep going. We're looking for one that is stopping. There we go. So number 8. It's also not super stationary. Number 11 doesn't. This one doesn't look busted to me. It looks like it had a nice life. Yeah, that's not stationary across its range. Okay, that's an interesting possibility. Just want to make sure that the ready particles aren't what I'm seeing. I shouldn't be seeing any ready particles. And it hadn't occurred to me, but maybe the way I set them up to draw, it doesn't check their state, it just checks the begin and end, and maybe, just maybe, even if I only send down 1 point, it's still doing something, which would be not what we want. So, let me see, how do I transform? Here's how we draw the tail. Yeah, let's just look at a breakpoint right here. We're going to look at the particle we're trying to draw. We're going to see what happens when we get a ready particle. There we go. There's a ready particle. And so the ready particle has set up a trail. And C0 has 1 in it. Is that really correct then? Kind of feels like this. Trailhead is not less than trail end. Count minus trail end. Yeah. Let me draw a diagram. I think that's going to help in this case. We're going to draw a little picture of how we're using the buffer. Whoops. All right, give me a sec while I rearrange and go into drawing mode and pick up my mess. Okay. That'll have to work. So I have a position buffer like this. I've got a head pointer and an end pointer. Initially, I have them both looking like this. So this is an empty buffer, right? When head equals end, it should be empty. Then what happens is I start writing into it. I write once. So this has one element, two elements, etc., etc. This has one. Let's see. 1, 2, 3, 4, 5, 6, 7 elements have been written, right? So the head is always pointing at the thing that's actually been filled. Now the weird thing is the end right now hasn't been filled. So I think the confusion here is that end. I don't know how to make. I'm trying to figure out how I want head and end to be oriented in terms of inclusive, exclusive. Right now, what's happened is, and just in case it's confusing, the reason head grows forward and end stays here at the end instead of being, like, you can imagine that what needs to happen is the end goes right here, and this is how we initialize it. So the head is right here. On the first write, the head moves forward one and writes into this spot, and the end stays right there, right? But that's not the way it's working right now. What's happening is, I think it's probably the draw is inconsistent with the writing rule. So let me just design how this should actually work. What should happen is I've got 1, 2, 3, 4, 5, 6, 7, 8 slots in my buffer. So I should be able to have a trail with like a current position and 7 previous positions. Let's say when I filled all 8 spots. Well, let me see. If this is empty, so here's an interesting thing, right? How many elements? Let's say how many values are in the range, right? And the answer could be anywhere in the set from the set of integers between 0 and 8, right? I could have nothing inside my range. I could have 8 things inside my range. I have a buffer of 8 slots, so I want to be able to have 8. This, of course, has a cardinality of 9. What I mean by that is there are 9 different counts. BYP, that sounds awesome. BYP says that there's a post by Fabian that explains how to do this by distinguishing between 2 spots, by tail and tail plus n. Could you link that? That sounds like something I want to pull up right now, because that's Fabian's the exact right person to solve a problem like this in a blog post. I haven't seen the one you're talking about, but I've seen a few other ones like rounding and stuff like that have helped me a lot with similar problems. All these, like, how do you get the finicky integer logic just right? Because what I was going to say, while I'm waiting for that link to come in, what I was going to say is that if you think about it, say I've got the head growing here, so I have 8 spots I can put the head. I have 8 spots where I can put the tail, or the end spot, right? 1, 2, 3, 4, 5, 6, 7, 8. But I need to actually signify 9 different values. And so I've run into this problem where I either have to have 0 or 8 fall off the options. Either I can never actually have an empty buffer, or I can never have a full buffer, right? So if I set it up like this, for instance, where I've written all of these, and then end goes to here, then I have to say, if this is exclusive, I've only used 7 spots. Now I've got 7, and this would signify empty, right? And then there's 1 element that is good, and these are all dead, and so on and so on. So I need some kind of solution that's a little bit... I need a solution that's a little bit more smart, and now that I see that there's a limitation where I can't just use head and end because of the mismatch between the number of states that I want and the number of states that I've allowed myself to have, I need a smarter solution. So let's see here. We're going to check this out. Ring buffers and queues. Let's see what this says. Also, how long are we dealing with here? Okay. So it's kind of long, but let's read through it. This will be, we'll get to learn. 14 years ago. Wonderful. The data structure is extremely simple. A bounded FIFO. FIFO as in a queue, like what we're doing now. One step up from plain array, but still it's very basic stuff. And if you're doing system programming, particularly anything involving I/O or directly talking to hardware, it's absolutely everywhere. It's also very useful to communicate between different threads. I have some notes on the topic that aren't immediately obvious, so it's time to write them up. We're going to talk about single producer, single consumer case, since that's what you usually have when you're dealing with hardware. The producer produces commands, objects, whatever, in some way and appends them to the queue. The consumer pops an item from the start and does its work. If the queue is full, the producer has to wait. Okay, so this is a little bit extra. I'm not really doing a full producer consumer thing, but it's sort of like I'm going to build one layer on top of this. So I'm taking this idea, what I'm trying to build uses a generic producer consumer in a specific way, but I don't need to bake that in just yet. This is what you normally have when talking to hardware. In this model, the 2 positions are just array indices. When adding an element, you first write the new element to memory via lm right position equals x, and then compute the next right position. Right position plus 1 modulo size. Reading is analogous. If read position equals right position, the queue is empty. Otherwise, the queue currently has right position minus read position elements in it. If right position is greater than read position, or right position plus size minus read position, right. There's an ambiguous case, though. If we fill up the queue completely, we end up with read position equals right position, which is then interpreted as an empty queue. Storing right position minus 1 doesn't solve this. Right. There's a simple solution, though. Don't do that. Seriously, when adding elements to the queue, block when it contains size minus 1 elements. What you definitely shouldn't do is get fancy and use special encoding for an empty or full queue and riddle the code with ifs. I've seen this a couple times, and it's bad. It makes lock-free implementations hard. You say usually have no locks if you use okay. That you're not giving the actual position in the ring buffer, but the distance traveled from the start. So if you've wrapped around the ring buffer twice, your current right position should be 2 times size, not 0. This is just a slight change with important consequence. Writing elements is updating the inner indexes. In other words, you delay the reduction modulo size. For this to be efficient, you normally want to pick a power of 2 for size. This makes the wrapping computation cheap and will automatically do the right thing if one of the positions ever overflows. It's very straightforward. Okay, so the idea here is we would not ever actually store the right position or read position wrapped. We would wrap them on demand. We would take the modulus when we're doing the indexing. And then since you're now doing modulus every time instead of, well, I mean, here you're doing it every time too, but you can put this inside an if, and it's doesn't have to be a full divide very often. This, you have to do it every time. And so if this divide is by anything expensive, if this divide is expensive, you have a problem. But you can make divides cheap if you use powers of 2. That's the idea. All right. That's cool. So I'm thinking about if I want to do it that way. I don't want to get stuck here. This is a low level detail. The easy thing to do would be to just say let's add one more element and let the do the case where I'm wasting one slot. In my case, my slots are very small. We're talking about 8 bytes. So I would allocate an extra 8 bytes just to allow the wrapping per particle. I'd allocate an extra 8 bytes per particle just to allow the inside the position buffer. So for a trail length of 16, I would expect, for instance, that I would need to allocate 17 slots. And then when head equals end, it's empty. And otherwise, it's head minus end modulo the size of the buffer, essentially, right? Okay, I have internalized that. Let's do a quick pass over the particle stuff. So here we initialize it to empty. Here what I'm going to do is I'm going to say if all right. So if the trail is full, the way we check that is if the number of elements or the number of values in our trail is one less than, or if this plus one more would fill the whole buffer, then we're already full, right? This is the case where we're full. So it's not this, right? Because then we have that ambiguous case we need one more. I guess I could express it this way. If the number of elements or the number of values in the trail is one less than the number of slots in the buffer, why don't we actually rename that like this, trail count. So slot count, trail slot count, trail slot count, trail count, slot count, trail count, slot count, slot count, trail count, slot count, trail count. Okay, from here I can just do it like this because I've got past the spot where I used the name twice. All right. There we go. Very good, very good. Nice. So we initialize, we start the particle here. Position delta. Okay, when we're stopping. If we were moving, we set to stopping. Once we're stopping, we start incrementing trail end. And then here we're checking the condition for when we're empty this way. So when the trail is empty, we set it to ready. Cool. Now, when we go to draw, the way I'm going to do this is if PRT trail head is greater than PRT trail end, then trail T0 is trail plus trail end. Trail end all right, let me think. Tiny little eraser. How do you get... There we go. Yeah. Okay. trail head minus trail end. So that's, if that's a 0, and that's an 8. Oh, that'll be a 7. Right, okay, cool. Now, if that's not true, then what happens is we're in a we want to check if we're in the case where trail head is less than trail end. Then this is still trail end plus 1, but this is going to be trail slot count minus trail end, I believe. Let me take this stuff back a few steps. If I have this here and this here, then these are the dead ones, and these are the two ranges. So end would be at a 6. This would be at an 8, so I think it's 1 less, right? Since this is excluded, if this is at 6, then this, yeah. Another way to think about it is it's like this, right? Now this is just going to be the start from there, and C1 is going to be head plus 1. Oh no, I've been tricked. Applied all this inside of the wrong one. Okay. Okay, wait, this is the right stuff over here. Okay, let's make sure flow effect is out of the picture. Okay. All right, I think that fixed it. Now I'm not seeing any buildup of the little dust particles here. I think those were particles that had died. When they went to the drawing, they were, even though everything else was consistent, when it went to the draw those particles, it was treating them as if they had 1 point, even though they were supposed to be empty, right? I was inconsistent about what trail head equals trail end meant in such a way that for the drawing procedure, it was drawing 1 point, and for everything else, it was thinking of that as empty. All right, I'm gonna take a 5-minute break, leave you to watch this cool little flowing thing, and then now that that bug is fixed, we'll get on to the big show for the rest of the day. Trying to figure out how to make this programmable so that you can have more than just this particular equation in animation. That'll be the goal when I get back in about 5 minutes. Okay. Now, what are the controls going to be for changing the differential equation's parameters? We have a couple of hours to play with this today. One possibility is like the most powerful possibility would be to allow the user to input an expression and essentially interpret that convert it into a tree and evaluate that, or turn it into bytecode or compile it or something like that. Right? So we could play with that idea. You put in an expression and parse it. I'm afraid that could be more than what we can do in a few hours. I don't have an expression parser to just plop in that has arithmetic and all the bits there. We wouldn't need to be too fancy about it because we know we would be dealing with floats only, so there wouldn't be a type system really, or the types would just always be float. We could go with something very simple like, hey, it's not math expressions, it's not set up to be pretty, it's set up to be regular, like a Lisp type shape or something like that. Something very something that would simplify the parsing. But even that, I'm like, well, that's not a very fun way to type in the expressions. It doesn't make a very, very, very good interface. On the flip side, doing a visual interface over here also feels pretty tough. Like, we could do a drag and drop button probably and have like hard code. There are 4 parameters that control this particular system, and we could, hand code up the we could hand code up the parameters there. I actually want to see something. As I was talking about it just now, a funny idea occurred in my head, and I was like, what if there was another parameter in this that was like this? Just what would that look like? Oh, that's pretty cool. That seems unexpected. Ah, I dropped the negative accidentally. Don't do that. So if I had a cool UI system to just use, what I think would be the most fun is if I could just drop in a text field, right? If I could just drop in a text field for the delta x and a text field for the delta y, and let you just change the expressions there, then that would be the most fun thing I could do. Because then you could in real time modify the expression, and whenever it parses to a valid expression that it can evaluate, you just see what your system looks like here. I think doing a bunch of hard-coded systems, so I did this yesterday. I did the Lotka Volterra thing, and that's cool. But doing a bunch of hard-coded ones, like if I were going to do this on the command line, so that you're going like diffy qviz, or maybe I call it delta xy plot. Yeah, I could call the program delta xy, and then Lotka Volterra, and then 1111, right? So that would be like setting each of these to 1 and using this function here. So we could go down that path, and then like we could say like, okay, let's have delta xy. When you do it this way, it will just on the command line spit out list of forms. When you do this one, it would begin the plot. Of course, what you don't get for this is you don't get to see the animation. So another idea I have here is, what if I let you compile a separate DLL and plug in your function yourself, right? Because then I could ship it with the DLL for a few of the demos, and then you could just build your own, and these DLLs would be super, super, super simple to build, because you just basically are making a function like, not even like this, you'd be making a function with like a P and a T parameter. You know, I could send you the T parameter, the number of seconds that the animation has been running, and you could use that. And then it's up to you how you use the T parameter and the P parameter. I guess the other thing you want still, okay, so what if we did that? And so you can go, and we still want BYP has sent me a link. It looks like something I want to check out, but I probably can't do it on stream right now while I'm taking my last few hours to try to make this useful. Let's see. Right now I'm still using hard-coded abstract space, but you can imagine that I'd do something like that, and then I could do the abstract space, or like we could do, what is this, the like range 0404. Something like this, right? So then the idea would be this would become so the difference here is that right now the form only contains like the mathematically static idea, and then I'm doing params. So what would change is this whole thing here is what would be determined by the DLL, right? I'd put all of this into a DLL. So the parameters, the function choice, and the possibly animation of the parameters. So you have to be able to build that as opposed to trying to parse something like this. Let's just see what it would look like. I'm going to just think it through real quick. So if I were to say, hey, I'm going to do a parser, and so you want to say something like, all right, what are the chances I can write a parser for something like that that is good enough in the next couple of hours? We wouldn't have variables, right? We just have x, y, t. We have the built-in functions like sine and cosine. We need a plus, minus, times, probably a divide. You need to be able to parse a number. We're talking about doing a lexer and a parse tree and then an evaluator. That seems hard too. I don't know. A part of me is thinking that the simple solution here is to go to list of forms delta xy form params. This, I feel like it's definitely playing it very, very safe to do it this way, but I think I can get more out of it trying to do this than the DLL thing's gonna be kind of clunky and not fun to play with, and the expression thing is too hard to accomplish. So I think if I do it this way, even though I won't be giving it full programmability, I'll be able to actually get people like something that they could type in and have fun seeing the animations pop out. And if I do anything else, I just don't think people would have any incentive to play with it, because it'd be either I won't finish it or it'll be too much to ask for. So I think I'm gonna go with this, even though it's not all fully programmable. And that'll mean we're going to lose the ability to do animations. So this was cool, but this would have to come back some other time. Since it would require expressions to even be able to animate those. I could maybe bring it back by putting in like an option to wiggle a parameter. But this is still cool. All right. So what we're going to need is, what's the data structure that I can use to represent the list of forms and the parameter structures for each one? Let's start there. The data structure is going to be something like I'm going to make a list of these. There's just going to be a linked list of them. It's going to have a name. It's going to have a list of parameters, which each come with a name. All the parameters will be floating point numbers. And it's going to come with a diffeq function, which is the function that you run if you actually selected this one. Okay? And then we're going to need some form construction helpers here. We're also going to want a form list type. So we'll be able to say here's the arena we're building our form list on. Here's the list we're building. Here's the name and the diffeq function. You give me back the form, and then I can go diffeq viz form param. Again, I give you the arena. I give you the form you want to attach this parameter to, and I give you a name for the parameter. So that'll let me build my form list like this. We go, here's the form. One of those, that's what we're going to return at the end. The name is going to be a copy of the name you pass me. The function will just be a function pointer, and then we'll stick onto the list that form there. Okay. And then here, similarly, we're going to construct a parameter. So we'll allocate it onto the arena. We queue it up on the forms parameter list. And again, copy the name on. All right, so if you're following along, if you see what I just did here, this right here is why I love Arena so much. We can just build interesting data structure constructions like that. And so now watch. All we have to do is just say like, okay, this here is going to become our form data diffie qviz form data structure. So this is how we're going to do that. We're going to stick this right in here. Form options like this. You know, just like that. It's done. And so now during, actually, you know what? I don't even need this in the variables. What I'm going to do, it's technically going to be constructed dynamically, but we're going to do this down here. Let's see. The arena comes in. Yeah, so before we even do vars, here we're going to do command line options. Okay. Now this is going to be weird. Let's get ready to deal with the weirdness. Diffie qviz is currently set up as a graphics program, which means if I were to printf, right? And actually check this out. So I don't do printf anymore. I do m4 mod printf, I believe. Mr. Fourth base standard io.h. Hello world. You can see I don't actually get to see what came out there. So the reason for that is this is a graphical program right now. And so it's not going to be happy about the fact that I'm launching, that it's not going to let me do standard IO stuff, right? It works if I do it in 4Coder, but over here it won't attach to the command prompt. So there are a couple ways we could deal with that. One is we could finagle this to be a command line program instead of a graphical program, so that it will actually use the command line that runs it. In order to do that, I would have to make the following changes. This would become main instead of win main, and this would have to go away, right? So watch. If I were to come over here and say no, not win main, int main, you know, I can never remember actually. Yeah, okay. So if I do this and then this, it won't build because we've specifically told it that we are building a graphical program when we talk to the linker. But if I were to do this, then the problem is going to become, it's not going to link in these things. So if we go over here to my linker flags, you can see I have, if it's set up to be graphical, it does subsystem Windows. If it's set up to be console, it does subsystem console. What I kind of want is like a console graphical option, and that'll be for telling it, hey, set up as a console program, but also still do these graphical things for linking. See if that works. There we go. Now if I do this, I get my window and I get hello world. That's cool. Let's do some other things. So this is going to full screen. I actually don't want that. Everywhere where it talks about video width and height, I'm going to have to change it. So let's drop those and deal with the consequences. So here, raw geo. What I should actually do is tell it the dim, you know, windim here. So instead of video width, it'll be windim x, and instead of video height, windim y. This is similarly gonna need the windim. You're gonna need the windim. I guess another way I could have done this is to just keep the macros, set them to like 800, 600 or whatever, and requested that window size, but I just want it to use the default window size, honestly. There we go. Except now I'm thinking like, oh, it'd be cool if I did the whole thing as a square. So let's go back here, graphics, set, interact. Let's just do it like this, right? Now that might not be good because it might actually place it at 0, 0. Yeah. So what I'm going to need to do is I'm going to need to get the inner rectangle. And then I'm going to take the center. And then I'm going to reform this as this. And then I'm going to set the interact like that. There we go. We can set the title. Delta XY plotter. Boom. That's pretty fun. Okay. Now, so this worked. We can hard switch over to int main. We're doing command line. We don't need to do hello world anymore. Instead, what we're going to do is we're going to say step 1, build forms list. So we built this data structure, where we defined the data structure. We're going to build it in a second here. And I want to just fill it in with all of the forms. Right, so that creates the form, and so we can capture that as a pointer. And then we want to do qviz form param arena form straightlit. And so these are prey growth, prey predation death, predator death, predator predation growth. I want to go make sure I get the labels here correct. Right, I'm going for something here, like structurally now. So I might start getting a little fancy for fun. Something like this. So here where I define this, we're going to do name description. Come up here and say the parameters come with a name and a description. And also the form is going to come with a name and a description. So here's the name, here's the description, right? The function lives here. The description is going to be do all lowercase on these things. Predator, prey, model. Let's put in a default value on each of these. Okay. Now up here, where we're copying names, we just start grabbing descriptions as well. And in this one, we also want the default value. Okay. Is that the naming scheme I went with? PADB. Yep, that works. So in addition to a description, I'm going to give the x equation and the y equation like this as strings. P times x minus a times x times y. This is minus d times y plus b times x times y. Right? Dx equation, dy equation. And let's see here. These go up here. Dx equation, dy equation. Okay. So what we'll do is we'll build all that and then process command line arguments. Okay, so if I remember correctly, somewhere around here, command, I don't know if I have a helper for command line parsing yet. Anywhere, base h command, I have that, and that might be all I've got. We should definitely make a to-do to build a little command line. Yeah, I just don't have anything. Okay. This, I'll take, all of this stuff here. All right, I just remembered that they're doing fire alarm tests today. You might hear it again. I don't know. If you do, don't worry. I'm pretty sure that I am not having a fire in the building, but I apologize if it's loud and disruptive. That might have been it. That might be all we actually hear from it. But anyway. What I was trying to do is I was going to say all of this goes into Viz. Like this. And And I'm just going to have arena and frame arena kind of hang out like this. Okay. So what's going to happen is we've taken the command line arguments here. If the node count is equals 1, how do I want to do this? Let's see. I think the good way to do this would be like this. We grab a node. Now we're going to start doing things like, okay, form node. Skip the delta xy plot .exe. Extract form name. Select a form. And to select a form, what we'll do is we'll scan over all of the forms in our list. Right, so we have a form list. Start at the first one. We go if straight match form node name. Right. Don't worry about case sensitivity. Then the form equals the form node, and we break. Now, once we have a form, we're going to try to spend the rest of the time selecting out parameters. If we don't have a form, Okay. Um, then we'll do a loop over our. Okay, I think it's done for a bit. We'll see. Okay, hopefully the noise is done this time. We'll see. Nice. All right, this is starting to look good. I want the, so if you look at this, probably gonna get interrupted again, by the way, but if you look at this, I like this, but I think if I'm gonna have like 6 of these options or something, I don't necessarily want to print all the details. So this would be like the verbose version of the list, but I just want a version of the list that's just the list of names, and then the ability to like get full details about one, or to print a verbose list. So I'm gonna make a few options there. The default will be, if you don't get a valid form, that you just print the list of names. So that would become like this, simplified back down to this, right? So that's the list of forms in the non-verbose mode. Let me now pull out, we're gonna do print form. I'm not even gonna hope that it's done, but it's done for a minute, so let's see. I'm just trying to set it up so I can easily set this. Right, so if I do that, nice. Nice. Okay. All right, we're 2 hours in. I might have time for another hour to another hour and a half. I think with that much time, I should be able to finish this command line input system and hopefully put in a few more good forms, and that'll be what I have for the jam. Um, so you'll be able to pull this down and model out a differential equation out of one of the classic options that I pre-installed. And then once the code is live, of course, you can go in and program in your own equation or put an animation in or whatever it is that you want to do with the extra flexibility. While we're taking our time slot break, it's a good time for me to remind you that you can help support the kind of work I'm doing on this stream and all the kinds of projects I do. You know, if you go over to my blog, you'll see some stuff that I do, and I describe some of the stuff I'm working on. I've been working on Mr. Fourth Base off stream a lot in the last couple weeks. It's coming along pretty well, and I've got one of these coming soon. So yeah, there's good stuff going on. Your support helps me to keep this going, and it also gives you access to the source code before I'm able to get it out to everyone else, which could be a week or two from now. So if you're liking what you're seeing and you want to put in your own equation, that's something members can do. So there you go. Okay, so if I want... Then we will move the form name over by one. If we get a form and we're in details mode, then what we do is we have print specific form becomes the form, right? So now I should be able to do something like diffeq details Latka Volterra, and it gives me the details of the Latka Volterra. Okay, so there's the basic stuff that I wanted. Now I need to do the parameter parsing. If we are okay, so we're doing a visualization and we have a valid form. Then what we need to do is we need to prepare the visualization parameters. So the visualization parameters are like this. We need a diffeq function, and we need diffeq params. The diffeq function can come right from the forms function at this point, right? We've got that much. But now we got to figure out how to fill in those parameters. Now, the parameters is going to be allocated onto the arena directly. So we're saying they're all floats, and the number of them is the parameter count of the form, right? So we know that's how many parameters we need. They're all 0 initially, but that's okay. What we can do is we're going to loop over the parameters now. And for each parameter, we're also going to have an index going with it, so we know that these line up on the index of the parameter block here. Param first. The indexes are going to go like this. diffeq params index is going to be the parameter's default value. And now what we want to do is we have this this node pointer. And what we're going to do is if the node pointer does not equal 0, not here, here. If the node we have is not 0, then we're going to... Do I have a helper yet for getting an F32 from a string? I doubt it. I doubt it very much. All right, we're just going to hack one into this program for now. All right, so this will gather everything before the period. If we find a period, then we're going to stop right there. And then we'll have a second loop using the same control structure. But now, if we've reached this point, we know we've seen and consumed a period. So what we'll do is a little different. We'll go like this. This is extremely inaccurate, not a good way to do this kind of thing. Don't do this if you actually really need to convert strings to floats, but I'm just hacking it together here. I guess another thing we can add here is if the first value here is a negative sign, then we can be prepared for that. Like this. Okay. So if I run this, we get that. If I, how do I want to do this? I guess I'll go into remedy to actually see this. We'll say Latka Volterra 1.511 0.5. Okay. And then I want to see default value. Default value. I want to see this. So we're parsing out parameters here. Okay, so 1.5. Okay, so that's kind of working, except should be like this. So now I get 1.5, 1, 1, 0.5. So when I'm done, if I go down to here, I should have diffie q params. Looking good. That's the right parameters that I put in. So if do visualization, then I'm going to pass in those visualization parameters. So what are those again? Do visualization, diffie qfunc, diffie qparams. Grab those guys, stick them right here. And then we were doing this. We were saying every frame we would initialize these. I'm going to just move this. We're going to say after we've initialized the variables, we have to set the diffie q func and params. And so this will just go like this. Diffie q func, diffie q params. So now, if I just do this, interesting. Why did that happen? Do visualization. So if I run it with no parameters, I just get the list of forms. If I run it with just that, I get the default parameters. If I want to, I can then go, okay, that was cool. What if I want a growth rate of 3 and a death rate of 3 and then 1 and 1? And then we get like shifted over, right? Cool. Okay, so that's a good setup. Now, I think what will be fun is if I put in some more options. I also feel like I need a I also feel like I need a quick break. I need a quick I need a quick snack break. So be right back. I'll answer your question when I get back. Okay, so a Felix 5 asks, what type of discretization do you use? Discretization. um, in other words, the math of these equations is defined over real numbers, but to simulate them numerically, we turn them into some kind of computable thing. I'm not doing anything fancy. I'm just using 32-bit floating point numbers. It's not really an area of expertise for me, numerical precision stuff. So there's a very real possibility that that the visualization has a certain amount of discretization error, and I haven't done much about that. Time-wise, oh, sure. So the I mean, yeah, it's not that fancy either. I have a rate parameter. I'm just doing one update per frame at 30 frames per second, right? So the video is running at 30 frames per second in the output program here. Like if I do this runs at 30 frames per second. Each frame, the particle looks at its position and gets the velocity at that spot, and then it does that velocity times the rate parameter divided by frames per second. So if the rate is a 1, then that means we're interpreting the velocities as delta delta unit per second. I actually have the rate turned down a fair amount, so we're doing, what is this, delta unit per 5 seconds. But I just adjust this rate to get a speed that looks good. If I wanted to increase the precision on the plot, then what I could do, which is what I think you're asking about, so I could say something like this. First of all, okay, let's change something here. So we're doing this position delta thing here, which is totally unnecessary. Let's just do position add P. This will simplify the thing we're talking about. Next P. Instead of adding, we just do P dot X. We'll just do P like this, right? And then yeah, that's pretty much that. So that would be position add. Right. That would be the same as it was before, except now the API is set up so that if I wanted to, what I can do is I can go v2 f32 next p equals, just start it here, for instance. Actually, we could do it like this. You start with p. We then do, some number of reps. Updating p at each step. And then we take this and we multiply out by the number of reps we put in there. And then instead of next p on all of these, we would just go p. So we're updating p in place. We'll let it set the velocity out so that we can check the velocity where it ends. And then you get this. I don't know that, it's obviously different. No, this is not doing anything fancy like an implicit integration. I'm just doing the numerical I'm just like making a numerical estimate to create the plot. That's all I'm going for here. Nothing super precise or high powered or anything like that. We're also doing a 3-day jam, so I'm spending what, like 9 hours total on this. We're on the last couple of hours here. So, yeah. Nothing that's going to take too much out of us in this project. But I don't really see any difference between those two. You know, doing a finer grain step there. Not seeing major difference for me. Now, what would be good, before I go and add in some other forms, it would be good to have the ability to change the box, because right now the box is just a fixed. The box and the rate are just fixed details here. So let's go and see what it would take to change that. All of this stuff here labeled abs min, max, and rate. These are the ones that I think we could afford to pull those out. So yeah, let's just start by blocking them so we get compilation errors. And then like right here, I think we'll put this all into the vars. So the vars will know, in addition to everything else, we'll have abs. We'll have rect f32 ab space, or equation diffy. Let's call it diffy q space. How about that? Right. So the diffy q space, we'll have var. This just becomes vars diffy q space. Diffy q rate. Diffy q space x0, x1, y0, y1. That's it? Okay, cool. Diffy q func. Now, during that initialization period there, I'll throw those into diffy q space, just rect f32, min x, right? So we're looking at like 0, 0, 4, 4. Vars diffy q rate 0.2. So those are now something we might want to be able to pass down a little bit better. So this would be like diffy q space, range, maybe chord range, like this, coordinates, range, space, equation, viz params maybe. So this is the space we're visualizing. This is the rate. The viz params goes here. Break again. Viz params. Viz params. Viz params. Viz params. Viz params. Viz params. You know what? Actually, if we have the abstract pulled out anyways, let's just use that. Nice. All right, so then we want to put in the extra options for configuring those. So set coordinate range. If we find a range like this, then I'm going to go okay, so I do this, I get this shape. Now, what if I look at this and I go, you know what, I'm kind of feeling like we're too zoomed out. I want to get a little closer. Let's set the range to 0, 0, 1.5, 1.5 and see how that feels. All right, cool. What if I'm kind of like, I'm curious about, I'm getting curious. I'm like, what's on the negative side of this plot? Obviously, the negative side isn't meaningful in a predator-prey dynamic because we shouldn't have negative populations, but I haven't seen these corners yet, and look at that. They're cool. This one has the spinning effect where the interesting stuff happens, but these do interesting things too. Are these also spinning somewhere way out there? Or are they just sort of arcing? Like, are they more like parabolic? I'm curious. So now I'm like, okay, fine. Okay, interesting. What if I go like -5, -5, 1, 1? What do I see? Okay, that doesn't have it. -5, 0 to 0, 5. What's in this? Now we're looking at the top left. Yeah, so it's like, but it's not circling around. Cool. This is cool. This is cool. 0, 0, 100, 100. Now it's all insane and it's out of proportion. Okay. So now the other thing here is, what about the rate of motion, right? Because these are cool, but I also want to be able to control how fast it's going. If I'm zooming way in, like if I'm like, hey, I want to get really close to that, the point of equilibrium there. Then the next thing I'm thinking is like, can I set it to like change the rate as well, right? So let's put that in. That would look kind of like this. Except we only need one of these. And we're setting the rate. Cool. All right. So I kind of want to do something like this. I'm going to have the default range be like super typical stuff. The pH test, could you have the colors correspond to velocity? I suppose I could. A part of the reason why I'm doing the all the different random hues is because I mean, I guess I hadn't thought about it much. It doesn't do anything for us right now except to give your eyes different things to latch onto. And if it was black and white, it'd probably be just fine that way too. Like I could just drop the saturation like here. There's nothing stopping us from trying it. Right, I could just take the saturation values and be like 0 saturation. Right. And that's cool too. That's fine. I think. So here's a couple of things about the hue, changing the hue that way. One, the The trails don't keep track of, like, the trail system here keeps track of position over time. It doesn't keep track of hue over time. So if a particle's hue is changing as it's moving, I'd either have the whole trail changing its color. So like it wouldn't just like these purple trails here wouldn't stay purple if they were changing from purple down through blue and then green and yellow and red. Like the whole trail would change as the particle was changing color, and that might not be a problem, but I think it would be better if I was gonna do color changing on the if I was gonna do hue changing on the trail or on the particles, I would want the trails to actually sort of correctly track their color over time, so that I could, you know what I'm saying, like keep the trail acting like a consistent shape thing. The the other thing though is like I'm not convinced that's a good use of color. I already can tell the velocity of things by the flowing and like the length of the trails. So there's already visual feedback about the velocities in the visualization. And if I was gonna make color meaningful to the visualization and not just for being pretty, I would want to use it for something new, something different. Like what I did in the flow effect for the where I first programmed these trail things. I actually had each hue represented a sort of modulation of how it. So you could imagine that it's not just one flow field, but that it's an entire there's an entire unit disk worth of flow fields, and the unit disk is continuously mapped to these different flow fields, right? And so which hue you are would tell you which flow field to follow. And that was a cool idea for what hue could mean. But I don't know. I think my main answer is right now I don't have the easy ability to change the hues as the particles exist. The hues are kind of just a one per particle fixed thing. They're not changing over time. So that would be a new thing I'd have to add in at the low level to make that capability. And then I'm not actually sure what I would want to do with that information. I'm not sure that velocity is the most important thing. I could see like it would look cool if which direction the particle was moving. So it's not if it wasn't hue, or if it wasn't the speed, but like the if the direction of the if the direction of motion for the particle corresponded to an angle in the hue circle, and then I used that to create the gradient, I could see how that would look cool. But still, I'd rather keep the color meaningless, so that maybe someday I could come up with a useful way to use color, I think. Hi, damn you. Alrighty. So I can control the rate, I can control the range. The default here is like this, and I was thinking like, okay, if I first of all, this is only interesting if we're going to print the form list, and these are only interesting if we're going to do the visualization, so we can, well, it's always better just do the extra work, get all the information pulled out. What I want to say though is before these print overrides get applied, I want to have a default thing here. So viz mode, if I have a form, what I'm going to do is say, in addition to pulling out the parameters, the viz space stuff up here, the viz params should pull off of the form's default viz params, right? So then what I can do is I can go, okay, so we have this form thing, we've got all this stuff, let's put in addition to all of that, diffie q viz viz params, default viz params, and now what I'll do is diffeq viz form. The function is just going to fill this in default viz params equals dot space. It's going to be, I'm just going to put in a default for each of these, and then I'm going to use direct manipulation of the data structure instead of trying to, here I was passing these in because I want to like copy them onto the arena and like ensure that this gets uniquely set, no defaults for the function. So these all needed to be done. This is more like an optional thing to tune it up, and it's also a pain to put these parameters into a function because there's a lot of detail. So when I have high detail optional stuff, I switch from using a function to directly manipulating the data on these constructor things. So this is going to get replaced with the default being 0, 0, 4, 4, and the default rate being 0.2. So those defaults there and these defaults here are kind of linked together. If you do all your defaults, I want it to look okay. Right, so if I were to come in here and do this, I would just get, oh, that's not quite right. That should be showing me what am I missing here? Default viz params, default viz params, rect, space. That should be space. Right. So there we go. Our default looks cool. In fact, I could even see this saying like maybe the correct default here is like 0, 0, 2, 2. Or 3, 3. Yeah, that's a good default. Very cool. Now what I want to do is I want to fill in some more forms. So these were cool. These were good. We can set the range. We can set the rate. Let's go. Let's take another 30 minutes to an hour to find some cool differential equations. So that one is a classic one. What's another classic? I can also do ones with a single variable. And when we have a single variable, what we'll do is we'll just say y's are fixed. You know, they always have a velocity of 0, and we just focus on the delta x's. And maybe we can tune up to have, like, instead of using the whole box, it can use a thinner rectangle shape or something to make it more like a slightly spaced out number line. Like vertically spaced out. But let's see. Systems with So one trouble here is that I only have equations for velocity. I don't have a system for acceleration. So we could spend some time doing that, because like um, if I have to do this one, I would have to say what's the acceleration, and then I'd need to keep track of a velocity inside of each particle, and so this would run on a different principle than the first one, which would be kind of cool to support. Let me think of other things that work like this, though. Let's go with first order two variable differential equations. That's what we are supporting right now. See what we can find. So another thing I'm missing is I don't have the option for putting t into the equation yet, which might be a good thing to support. Okay. Yeah, let's add support so I can do like a linear first order generally like this. Okay, so to support things like that, what I need to do is I need to look at Right now, I'm telling it an x and a y value, but I'm not telling it a t value. Let's go ahead and add that in. So we're going to need to be able to figure out our t value right here. So F32T is going to be based on var's frame counter divided by video FPS times the abs rate, right? So that gives us our t value. And then when we go over here and look at our forms, the only problem is we need a t. This one doesn't depend on t. But if we wanted to, we could do look at some examples of linear equations. I don't want the general solution. I want an example of a linear equation. Not an abstract example. Let's try this. These aren't examples. Okay, let's try this. Here's the name of one I could actually use. All right, so I think if I'm understanding correctly, I can't quite tell what the variables and constants are here. All right, all right, all right. All right, let me see where to start. Let me try something. Let's forget the internet. Let's try a book. Here we go. Let's see. First order differential equation with homogeneous coefficients. Solution to a differential equation. Let's start there and see if we get any good examples from that. We are while I'm doing this, let me do this here. Let's see. We're looking for example systems. Here we go. Problems leading to differential equations of the first order. That might be what we need. So let's start at page 107 and explore there. Well, I know of at least, actually, now that I think about it, I know of at least one more of these that I can do. I think it would be fun to do second order. I think we could do that. And I think it would be possible to do a single variable one that would fit into what we already have. So let me do these. Okay, we know. What do I search here? I know this has a cool equation that I want. You get the 4 quadrants. Right. But where's the oh man, what do you call the continuous form of the replicator equation given by the differential equation? So here we have a first order of x, and it only depends on x, where xi is the proportion of type I in the population is the vector of the distribution of types in the population. Okay, so okay, we can do this one. Okay, now the equation is the change here is equal to the current proportion. So we're assuming these proportions are between 0 and 1 in this case. And the vector of the distribution of types in the population, is the fitness of type I, which is dependent on the population, right? So
the new xi is equal to the xi plus xi times ax sub I. That is, this is written in esoteric form. Where's the the proportion of xj times the fitness of xj fitness information for the population, right? So there's my fitness matrix A. Okay, so F could be a complex, like a nonlinear function when we turn it into a payoff matrix. We get the linear version. Okay, so what this is saying, this is written as like matrix notation here, but basically we have population A is going to be P dot X, population B is like 1 minus pop A, right? And then the new population A, or the change in population, the first population, we want to do AX sub I. So if our matrix is, let me write down the matrix. Right? And we're looking at multiplying that by, we have this vector here that's like pop A, pop B. So when we multiply those together, we would get AA times pop A plus AB times pop B, BA times pop A plus BB times pop B, right? So that's AX. Now, that first part there is just AA times pop A plus AB times pop B. A meets A times pop A plus A meets B times pop B. So that's this part here. Then we want to subtract. So we take that, and if we're going to do pop A, pop B. I guess it starts with a copy of this and it goes space that way out. Take this and space that way out. And then that goes there. And we want one more time. We get pop A times AA times pop A plus AB times pop B plus pop B times BA times pop A plus BB times pop B. That's our final thing there. So what I'm going to do here is give some names. This is the fit of A is this thing. The fit of B is B meets A times pop A. B meets B times pop B. This is now the fit of A minus the population of A times the fit of A plus the population of B times the fit of B. All of this is times the population of A, right? We take the current population of A and we multiply that by the payoff for population I and the mean payoff so we'll do that. We leave Y out of it and we can go pop into the list of forms here. So we have Locka Volterra 2 replicator equation 2 replicator equation 2 a model of the natural selection. This should be 0, or even we'll say empty. Y y prime equals, yeah, so you see right here we have assumed dx and dy here. This was a mistake. We're going to have to undo this mistake over time. If form dy equation dot size is greater than 0, then you print that. But what we've learned is once we want to do second order equations, this won't even be accurate anyways. We'll have to think about a different way of structuring that data structure. Now the equation here is x times payoff let's see, AA times x plus AB times 1 minus x minus x times blah plus 1 minus x times blah. Right, this is very quickly getting to be too much to write, so I'm going to just write payoff x and let's see, coming back here, we'll do a hawk dove defaults. So A is hawk. If we set v2 the hawk gets full resource v. A meets A, you get a payoff of 0. Taking their numbers here, V, C, and base of 4. So this would become negative 4 plus 4. This would become 1, 2 plus 4. So this would become 6. This would become 4. B meets A. So the worst thing to do is to be a hawk and meet a hawk. The next worst thing to do is to be a dove and meet a hawk. The next worst thing to do is to be a dove and meet a dove, because then you get 5. And the best thing to do is to be a hawk and meet a dove, because then you get 6, right? We only need a range like this. All right. So let's see what happens. Replicator equation 2. That's not what should be happening. The something's not quite right. First of all, d dot y should be 0, so why are we getting changes in y at all? Right, that's kind of weird. Oh, it's still using Lotka Volterra right here. Okay, what we meant to do is to use replicator equation. Okay. There we go. We can increase the rate on this a little bit. So what we're seeing here is X represents the population of hawks. And so if we start with all hawks, all birds who are willing to fight for food, then them encountering each other and fighting hurts too much, and they don't outcompete the doves. But if we have a population of only doves, of only birds who are willing to share, then when hawks show up, the hawks do okay. So there's an equilibrium point here in the middle. I wonder, 4, 5, 6, what if I just made these like this? Yeah. So this is an equation in a single variable, right? X is the only thing that's relevant. Y is just here because that's how our diagrams work. But now I can do things like, okay, what if I want to do a different replicator equation? Let's look at, so hawk and dove was cool. War of attrition, what are the, what's the payoff matrix here? I just need to see a payoff matrix. I can't do 3 population yet, but I could do it. We could actually do 3 population. Fortunately, they didn't give me another payoff matrix to play with here. But let's just make one up, all right? So, got Milton. We did a payoff matrix that looked like this. All right. We've got A, B, A, B. And then I did A meets A is 0. Can I get the info for that? Or not the info, the details. Whoops. Okay, so A meets A is 0. A meets B is 3. B meets A is 1. B meets B is 2. Right, so I did something like that. So your best option is to be A against B. Your worst option is to be A against itself. Right, it makes sense. You always are preferring to go up against a B. But the cost of going up against a B, or the benefit of going up against A, or the cost of encountering an A is worse if you're also an A. That's the way that this balances out to be interesting. So I guess another pattern that I think might be interesting to see for this kind of equation is, what if you're better off meeting your own type and you're always worse off meeting the other type? So what we get is an equilibrium point on either extreme. And then if we ever did anything that was just like strictly better to be A than B all the time, then you would expect to just see the thing shoot to the right, right? Like if we did, okay, if you're A and you meet B, you get a 1. If you're A and you meet A, you get a 1. If you're A and you meet B, you get a 2. If you're B and you meet A, you get a 0. And if you're B and you meet B, you get a 1. Then, it's just like, what are you doing? You want to be an A. A's work better with each other. They'd like to have B's in the population, but B's don't do well, so there's just no equilibrium with those. The thing with the spot equilibrium in the middle is when there's a high reward and a high cost together. Cool. Okay. So we got that one. Now, if we want to do 3 populations, we would need to go set up barycentric coordinates instead of what we've got right now. I would want a thing where, we could look at what it looks like in a square, but it would be more natural in barycentric coordinates, right? So what I basically was doing there was I was treating it is one variable, but there's two populations, and so the two ends from 0 to 1 represent the two extreme population options. And so to model three populations, what you want is a triangle where each vertex on the triangle, each corner of the triangle represents a population dominated by one type, and then the triangle itself represents the space of possible points, right? You want to be inside that simplex. Um, and that might also be a thing where we would want to spawn points in a different way. We wouldn't want to be spawning points outside of the triangle. We would want to clamp points to being inside the triangle. So I could add to-dos. Space visualization space one dimensional variant, two variable simplex variant, right? Another thing I want to do, though, is I want to explore the possibility of doing a second order equation. So a very simple second order equation would be something like x prime prime equals ax prime plus bx plus c, or something like that, right? Where a, b, and c would be our parameters. The trick here is these are all returning velocities. If I do one that's returning acceleration, how will that work? Well, let's play with it. I don't know if this will be a good idea, but let's just play with what that's like. So the first thing we would have to do is we would say, right now, we calculate v like this, right? We would want to switch to saying, actually, sometimes the particles themselves are going to carry their v value, and that'll always be initially 0. When we start a particle, set the v value to 0, right? And then diff eq kind. Set up a little enum here. It'll be like diff eq kind. So our first kind is first order. Our second kind is second order. And so we'll go, okay, this np equals v2 f32v equals if vars switch vars diff eq kind case first order boom 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 case second order. Here what I'll do is we'll grab the acceleration instead of the velocity, and then the new p-value let me just do the math here in my head. New p equals the p we've got plus delta t times the average velocity over this time, which is going to be the velocity we've already got, plus the velocity we've got plus the acceleration divided by 2, right? That gives us the average of those two things, which is the same as saying velocity plus half of the acceleration. And of course we need a new velocity as well. So the new velocity is the velocity plus wait, hold on. That's not right. Back it up. The acceleration is a per t, so we would need a times delta t there. And then when we divide it in, it would look like this, right? And then the new velocity would be the velocity we've already got plus delta t times acceleration. So we could say this is like v plus nv over 2. Here's our dt. All right, so that gives us our new position. Finally, the velocity we want it to test. Actually, I'm going to put the stop rule inside of the equation kind. Then we don't need to send v out. Right, so val can go back to being v. We look at the stop rules here. So if both of these are close to 0, then we'll stop the particle. And I also want the thing where spawning... Right, so... I don't know what this is here for. I want to do... switch on the differential equation kind again. In the first order case, we do this logic. Spawn equals. This is greater than this. In the second order case, it's acceleration. They might just be identical. But who knows, maybe I want this to be smaller. I don't know exactly. But with that said, now I can take a differential equation form here. Well, let's do another thing. When I create my form structures here, I'm now going to say, in addition to all this, we need the diff eq kind right here. So down on that function where we set that, we also want the diff eq kind. And then up here where we're filling them in, diff eq kind first order, diff eq kind first order. Now let's set up a form. Oh, there is another spot here. X prime equals, where was that? Yeah, it's this thing right here. This is the spot where we'll switch on the forms kind. And again, there's the first order case that we already have. There's the second order case that will look like this. Okay, now let's go and fill in a form for this. We're going to just do second order linear constants. And so this gets coefficients A, B, and C. interestingly, I don't have velocity right now, right? So I have to somehow get my hands on velocity. Now I just have to take that and stick it into my list of available forms. Order to linear constant. Just 3 parameters on this one. We're going to have the range go more like this, I guess. And we'll say that we want something like this, maybe. X prime, boom, boom, boom. Kind, second order, order to linear constant, boom, boom, boom. Did I forget anything? Oh, I did want to change one thing. When I go to print one of these, this logic here stops making sense if param description.size happens to equal 0. So let's see. If I do this, order to linear constant, give me the details. All right, show me the plot. That seems strange. First of all, it's shooting way past the edge, which it shouldn't be doing. Um, yeah, the NP here is still the new position. Why would you go outside of the range? This and only applies inside here. What did I forget? How did I miss it? Position. Okay, so diffie is 898. Okay, so I think most likely what's happening is I set the kind, but I did not set the kind in the variables. Yeah, there it is. Diffie kind equals diffie kind. Gotta pass that through everything else. Probably want to start thinking about bundling all the diffie info together. So that I don't have to, so I can just create all this in one spot. Qfunc equals form func kind. Okay. Okay. Yeah, so some of them are still escaping outside of the edge, even after I fixed it. Isn't that weird? Isn't that weird? Seems weird to me. Let's take a look at why that is happening now. Oh, right. Session order to linear constant. Boom. Oop, there's a mistake. So I don't know why this isn't doing its job, though. Like, this should still be catching all of them. So you gotta think about that, but this part we can see there's a bug. Okay, so now it actually saves new velocities. You can see some of them get killed on the kill line like they're supposed to be. But it's a mystery why some of them don't. do some of them shoot past? Also, is there any way at all to get this thing to do the turning around thing that I am picturing? Doesn't seem like there is much of a way to do it. Although maybe if I extended the range here. So let's do that. That. Yeah, I gotta figure out why these won't die. That seems like pretty important. Remedy. Please tell me about NP and abstract. Show me a case where you hit this. Okay. Show me some cases where you don't hit this. Alright. I just need to see cases where stop equals 0. You know, I also have another solution here. Let's do, run. Look at it. Stop. Space. Okay. Now I know for a fact that there are points outside of the range, right? Don't we know that? Like right here. How can it be that far out? I want to see how it gets this far when np dot x is less than -10. But we didn't set stop, huh? P's already too big. Right, it's already too far gone. And then I don't understand why it's not stopping. That just seems wild. Put me a breakpoint right here when np.x is less than -10. Okay, so this one is going to stop. All of these are in the case of moving particles, right? So right here, it's always going to grab that stop equals 1. But now it says stop equals 0. Did I accidentally declare stop? There it is. All right. So we can play around with our constants here. So we have a baseline acceleration to the right, plus a sort of coefficient of friction with this one. You'll notice here it's no longer a consistent flow field because different points at the same location can have different velocities. So there's actually like a different kind of visualization happening here than in the first order case. All right, that's cool. And what does it look like again if I ask for the details? Um, Neat. Okay. I'm gonna make that the default. 0.2, -1, 0.5. So we're looking at 0.2, -1, 0.5, the rate of 0.25. All right, now that we have that, we can do first and second order with one or two variables. I want to get back to this because there was a there was the appearance of headed towards let's try page 134. Problems leading to second order differential equations. Second order processes. Didn't find anything that I was super excited about. Let's try second order system of differential equations. Four springs, three values, beat the displacement for the rest position. M1 x1 prime prime equals negative k1. I think we could do this and eliminate k2 from the equation, right? We'll just have, or m2 from the equation. We'll just have two masses. Wonder about. I wonder about a pendulum or a double pendulum kind of situation too. I wonder if pendulum dynamics would be something you could make the plot of here. But so this would be like if I were to drop out this line. Is there any way to, yeah, this line and this line, and just keep this makes sense. K1, K2, K3, M1, M2. So 5 parameters which control, yeah, X and Y. Okay. So we're going to have two variables because we have an x and a y. And we're going to do three spring system. M1, M2, K1, K2, K3. Three spring system. This should be a good last one. This is how we can ramp up the jam. D equals D dot X equals, okay, negative params K1 times P dot X plus params K2 times P dot Y minus P dot X one, two, three. 1, 2 multiplies 1, 2, 3. 1, 2, 3, 1, 2 is the same. And then D dot Y. Oh, and this is all divided by params M1. Okay, so this will be negative K2. Right, so it's the negative of this part. Same force operating in the opposite direction. Plus minus params K3 times P dot Y. Is that right? I'm not entirely convinced. So we get M1 times the acceleration of x1 equals negative K1 x negative K2x positive K2 x2. Okay. Then we get positive K2 x1 negative K2 x2 negative K2 x2 negative K3x2. Yeah, okay. I think that's right. Okay. Last one. 3 spring system. You use 123 ask what code editor is this? This is 4Coder. Here, let me stop what I'm doing for a sec. If you want to learn about 4Coder, I recommend you go over to mrforth.com. Don't worry about the membership page for a minute. Go to my software tab on mrforth.com. Down here at the bottom, you'll read a bit about 4Coder. You can go to 4coder.net, which, I guess the security certificates are in need of an update over on this old website. You can find stuff here. And this is an old website at this point. The I made this editor like probably started it like 8 or 9 years ago now. I spent about 5 or 6 years working on it, and it is now being maintained and updated by the community of 4Coder users, and I'm not really involved in it anymore. But I worked on it for a while before I wrapped up my involvement. So yeah, you can also check it out on itch. Over here, it's still downloadable, the version I made. The community version has a lot of new fixes and stuff, so if you go to the Discord, you can probably get more good info about it. But to answer your question, 4Coder. Okay. Now I need some examples of the coefficients that we actually want here. It says 2, 1, negative, so 4, 2, negative, 4, 2, 2. Okay. So what's happening? Why, first of all, why does it feel like my three spring system is just moving in the X direction? It should be moving in the Y direction too. Um, hmm. Second order. Order two. Whoops, my bad. This should be the three spring system. All right, that's really cool. So I want to tune up the parameters so that I can actually see some oscillation behavior here, I think. I might also be looking at it across, like, maybe going all the way out to 10 is too much. Maybe I want to shrink in. Maybe like this much space. Let's increase the mass of the objects. That should slow down the movement of the particles. M1, M2, K1, K2, K2, K3. Okay. Yeah, let's just play with those constants for a bit. So if I do 1, 1, 1, 1, 1, we get this. It's doing all the overshooting. If I increase the masses to be really heavy, then things move slow. They still overshoot a lot. I guess they pick up a lot of velocity, and momentum still applies. If I strongly increase the force between the two weights, what happens? Now they shoot even harder towards the center by a lot. If I strongly increase the pull towards the walls, what happens? Now it moves. Man. So I'm wondering, maybe I need a bigger space. The thing is like, yeah, if I give them more range to move across, then it's almost like I gotta make these coefficients smaller because 0.5, 0.6, 0.6, 0.2. There we go. Yeah. I think I want to change the density rule. A little bit. I think there's two main parameters. There's density granularity, and there's like the density limiter. And what I'm going to do is I'm going to say we're actually going to look at the vars diffie kind, and for a first order equation, those defaults will be just right. For a second order differential equation, I might look at increasing the tolerance quite a bit. More. There we go. Yeah, so I've had this density rule, which made a lot of sense for first order equations because there's no point in having a big cluster of points in the same spot. But now, when in second order equations, velocity, the 2 points can be in the same spot and have very different velocities. So you don't want to eliminate them just because they're near each other necessarily. I still want some kind of density limitation, so I've put that in as a possibility for particles to die out and new ones to start. So you get like fresh systems spawning in all the time. Still fresh systems meaning like fresh particles with a zero velocity spawning in and exploring a new route. But we also want to be able to see the kind of like orbiting, the extreme orbiting of the system. You know. Now I want to just tweak the parameters a little bit more until I find something that feels a little less like perfectly symmetrical. Yeah, like this. Probably need to give it a bigger range, or I need to shrink all the constants down a little bit. Um, Cool. All right. So, in conclusion, oh wait, let me write those defaults in. Um, 20, 20, 20. Oops, wrong one. 10s become 20s. We want masses of 4, 2, 3. Oh, yeah, I want to play with, now that I've got that, what if, like, this mass is more significant? That's so cool. This is so cool. All right. We'll do that. So 4, 2, 3, 2, 0.5 will be our default for this. Drop the rate a little bit, build that, and now if I run it without any inputs at all, we get this. Cool. All right, I think that's a good stopping spot for today. I've been at this for almost 5 hours. Wow, really got into it today. I have other stuff I got to do. Got projects to work on and stuff. We're working on Mr. Fourth Base. We're working on, you know, working on these things that I talked about over here when I announced my membership program. So I got stuff to do for all that. The jam has been fun. I'll go do a little write up about that and try to get some of the code out for the jam sometime in the next few weeks. But if you want me to be able to keep doing projects like this for fun, as well as the research and development projects that I've got going on, do you think about going to MrForth.com and looking at the membership page? This is how I make a living doing this. So, there's cool rewards for doing it. You get to check out the code that I've been working on today before I take the extra time to finish packaging it up. You can also go and check out my the special Discord and get the weekly devlogs about what I work on and stuff like that. So think about that. Helps a lot, and I think it's worth it. It definitely lets me work on cool projects full time when people help out with that. So think about that, and I'll see y'all around the internet. Thanks for checking me out. Bye.